All right, so good morning. Today, the purpose of this video is to explain give an overview of the torque and balance lab activity. To start with, to do this, you're going to need a few things. You're going to need a meter stick. You are going to want to make sure that the 50 centimeter mark, and you know the difference between centimeters and inches. The centimeter, 50 centimeters, is marked, and also at the top edge it's marked at that exact point. 50, you're going to need a meter stick. You're also going to need 4 paper clips, large paper clips. Those look something like this. And then you're going to need a 50, 100, 2 200s, and a 500 gram mass, hanging masses. So this would be certainly more than enough, but that is what you need. Now, when you do this, I'm just going to give you a few overviews. Oh, and you also need one of these very, very highly machined devices. It was built in a science supply warehouse nowhere near you. And it's worth noting that this is designed for the meter stick to go in this crack, and then you want to line up that 50 centimeter mark that we previously referenced with the mark that's on here. This mark represents the pivot point of that screw head right there, because it's going to be pivoting on the screw, as you can see. Now, that's how that works. You are going to be balancing and basically hanging masses from, this is sort of a diagram of what we're looking at. You're going to be hanging masses from these ends at different places. The way you do that is just take a paper clip and then just open it up by rotating it like that. That's the best way to do them without breaking them. And then this big side can loop over the top of your meter stick, so it can hang like that. Can we see what we're doing here? There we go. And then this gives you a really nice hook then to hang your masses from. There's a hook, and it can hang very nicely. You are going to want to do this when you're balancing it, teetering it on the corner of a table is by far the best, with each end of it hanging not on the table. But this is the best way to hook those up. Now, as we move along, probably the biggest source of confusion is on this second page. So I wanted to quickly show you that. This is the second page of that. You basically will have done 6 trials. And by the way, another common question is, for these 3 predictions right here, these actually don't have to balance. We don't care if they do. It's honestly almost better if these 3 don't, because we can see a comparison of 3 that don't balance and 3 that do balance. And we can kind of have an idea of what's going on. To get over and to fill this out, to start with, I ask you to not do any of this until you've done this first level here, this first row all the way across. Do this one first, and then get checked by me, so you make sure you're doing it right. And to do it properly, you have got to convert. You've got to convert grams to kilograms. To do that, you really just divide this row by 1,000. Most of the time, you just put a point there, and it's basically dividing it by 1,000. This one would be 0.05. But you've got to convert that first column to kilograms. Since there's units in these columns, you don't have to put units here. But to get to newtons from kilograms, you multiply by 9.8, because that's acceleration due to gravity. And so this column would be kilograms times 9.8. And centimeters is going to be referenced from your point from your meter stick. Always look at the centimeter side. And your distance is going to be relative to 50. So you might have to do some arithmetic. So say you were at 70 here, and say you were at 30 here. Well, this distance is 20 centimeters, and this distance, although I drew it awful, according to these numbers here, would also be 20 centimeters. So you're going to have to do some arithmetic to figure out your distance, but that distance is from the pivot point. Your torque, this tells you all you need to know. Newtons times centimeters, you'll have newtons here. Centimeters here would be this times this would equal that. You've got to determine, is the torque clockwise or counterclockwise? So if we had a 100 here, let's say we had a 100 here, and then the 200 here, this 100 would be causing the thing to want to rotate this way. Even though it's not, may or may not be moving, it doesn't matter. This one would be putting a clockwise torque because it would be trying to twist this meter stick clockwise. And we're going to always just say, let's just consider we're looking at the centimeter side. Because if you were looking from the back side clockwise, it's going to be opposite. So always look at the centimeter side. You're always drawing it on the centimeter side. That's what clockwise, CW. Or in this case, if it's this one, the 200, would be making it twist the other way around that pivot point. That would be counterclockwise. So the diagram I have here, the 100 would be clockwise, and the 200 would be counterclockwise. That's how you'd fill that out. Now this is a little bit confusing. This is sigma. It's a Greek letter S, capital S. It stands for sum. And in this case, you're just going to have one of each. So this isn't really going to be a sum of anything. It's good. In this case, clockwise would just be whatever this number was. In this case, counterclockwise would be whatever this number was. Later on, I will say, into the lab, you get to the point where there may be a clockwise and a counterclockwise. And in this case, then you truly would have the sum of two that would go there, and then it would still just be one over there. But this is just a common way of thinking about it. You can add them all up. Even if you get a lot of different things going on, just using the sum of those torques works. Because farther on, you actually end up with a total of 4. And so you could have 3 and 1 or 2 and 2. So it becomes more relevant towards the end. I do believe that's everything. Thank you, and I hope it goes well.